Today, or the first talk today, the second one later on, is about modeling variability in requirements and test artifacts. Before we go into the talk, of course, I have to say something about the background. I said a little bit yesterday already. So I'm the director of Paluno, the Ruhr Institute of Software Technology. This is an institute which was founded 2.5 years ago. Already has about 100 full-time research equivalents, researchers, and 40 students working for us. And there are many areas we are capturing with the 8 full professors, and I just want to mention some of them. One is, of course, requirements engineering. This is what the talk's today about. And as you know, we have written a certified requirements engineering book together with Chris Rook, who is sitting in the front of the just reckon, and also is giving some presentation here. And you will hear a little bit more in the second talk today about it. Another competence area we have is variability management. And this is what the talk today is about. This is work which goes back to early 2000 till 2006-07. Where we had huge projects together with Siemens and Philips and other large companies like EADS and Thales and other major European player, where the basic idea behind this was to adapt principles which are applied in other engineering disciplines to software engineering. So what you will be hearing today is a thing which is quite old, but the way we deal with this in software is a little bit different than the people deal with in traditional engineering. So it is about product lines and variability management as one of the key assets of product line engineering. Then there are 2 new themes coming up. I don't know how many of you have heard about cyber-physical systems? 1, 2, so not that many. So cyber-physical system is a trend which is since 2-3 years very, very fast uptaking, especially in the US and in Europe, but also in Japan. And it's about the next generation of systems, which is systems of systems, where systems are composed on the fly to meet new demands. So you don't design the systems anymore, you just compose the systems as you go along. This is maybe a 2-second explanation of cyber-physical system. There are many interesting publications on this already, so I would recommend you look it up because it will certainly be one of the topics in the future. Future Internet application is the second area. This is in the European Commission and in Europe, so for research topic which is around for 5-6 years. It's now also taking up in the US. And it's very much about service marketplaces, so where you can buy software encapsulated services on the internet, and those services can encapsulate not only software but also people and other resources, and also the Internet of Things. So it's essentially about the conversion of Internet of Things, where you have real-time information about the physical things out there, so about your world. So for example, in a supermarket, the shelf knows what's in the shelf. You don't need a database to know about this. Together, the combination with the services, software services. This is the 2 areas below I want to talk today about. So it's mainly about requirements engineering and how you combine variability management with requirement, but also with test artifacts. I said that variability management is a key asset of software product lines, and there are many, many examples of product lines where software is key part of it, and where the principal idea of a software product line was adapted to software as itself. The principal idea behind product line is that you put it in software terms, you have a framework, so you have a core, which is used across all products. A common example you may know from the automotive industry 15 years back was VW, who first heavily applied this between VW and Audi, for example. So there have been times where Audi A4 and a VW Golf were 80% the same. You don't recognize it's 80% the same, but the parts were really 80% similar. So the principal idea behind, also for cell phones or for printers, but also for software systems like SAP, etc., is that you have a common core which is reused, and therefore you don't have to change it, and then you produce products based on this common core. And the reason why this is happening is the need for customization. In the consumer product industry, this need is around since early 70s, I would say. Really emerged in the 80s, especially in the car. So for example, when you buy a BMW, about 1 million BMWs, there's no similar one in average. So they all differ in some aspects, even if they share a lot of things in common. So in customer products, this demand was there for a long time. In software, I think it happens in mid-late 90s, where the pressure to also develop individual products based on a core and therefore much cheaper is emerging now, and I think it's still ongoing. It hasn't reached the zenith yet. So the principal difference between the normal way you build software, you write a specification, then you implement, then you test, and then you deliver, and it costs a fortune, is that you don't define the requirements for all of this, and you don't implement everything. You only implement the specific parts, and you reuse a core. And how this can happen, we will look a little bit in detail in the next 30 minutes or so. So what is product line variability? Product lines. Linda Norstrup, she was the managing director of the Software Engineering Institute for Carnegie Mellon. They have written the first book in 2001 about this, and they define software product line as a set of similar software-intensive systems. Of course, if they are not similar, they can't have a common core, which share a common managed set of features. What is a feature? Who knows, who have heard about feature before? Nobody? Thank you. Chris, what is a feature? You never heard about feature models? Really not? Okay, then you should read about feature models, I think. So, something to do at home. There's a publication from somebody who worked at SEI, who is back in Korea, and they invented it in the 1990s. It's called FODA. It's maybe the thing to start with. I even think I have a reference for this. So a feature model, a feature is an observable behavior of a product, observable for a customer, for a user, or for the system. So something the system does, which is a benefit for the world, which means for the user of the system. And a software product line is defined by a common managed set of features. Common means common to all products. We go in detail to this later on. And also which specifies specific needs for a particular market segment. So there's a trade-off between common to all products and still having the feeling it's my individual product, or it's individual for a particular market segment. There are two very easy things which differentiate when you develop software under a software product line compared with developing a product as a single system development. The first is there are two development processes. There's not just one, as you will see there are two. And the second differentiation is the explicit management and modeling of variability. I won't spend much time today on the two development processes, but we will spend, besides 2-3 slides, the rest on the management and the modeling of the variability. The two processes are roughly explained as follows. There is one process which is called domain engineering. And independent if you apply an agile approach, a waterfall model, or whatever development process model, so they all fit in this framework. Here it's a simple waterfall model, just for simplification, where you have the phases, like requirements engineering, design, realization, and testing. The goal of domain engineering is to make development for reuse, which means essentially to define this framework, to define the core assets, so the managed features which are used across all products, but not only this. But as we will see in a few slides, also the variability. In application engineering, the goal is different than in domain engineering, so it's not that you design a product from scratch and you do whatever you want. You use the assets which are defined in domain engineering, and the goal of the application engineer is really to build the software by reusing the things which have been developed before. This is a radical change for software engineering. To the students, I always say it's like if you work at a production unit where you fit together the cars. You only have different colors of the screwdrivers and different screws, but you have to try to do this screw in the hole you're supposed to do it. You are not allowed to change the hole, to use a drilling machine to make the hole bigger or whatever. You have to use it as it is. And this is for software engineers very, very, very difficult because they are normally used to do whatever they want. So in the product line, at least in application engineering, you are framed by the things which have been developed in the domain artifacts. This is a separate talk, so we don't go in detail in this. The important thing you need to understand today is that there are these two processes. In domain engineering, you design the product line and the common set of features, and in application engineering, you reuse those. The second thing, which is different than in the single system development, is the explicit definition and the management of variability. And there are two very easy concepts behind this. The first thing is what varies. So you have to define in your product line what can vary. For example, the color of a car. And you define this, we will see later on, as a variation point. So you define what varies, the color. And the second thing you need to define, also very simple, is how does it vary. For example, you define there can be red cars, black cars, and white cars. So no yellow, no green, black, red, and white. And what can change or what can vary is the color. So besides the commonalities, you also define how the individual products can vary. For example, in a mobile phone, the screen size, the memory you have, or some other things. Not that complicated really, but really complicated to make explicit decision what can vary and what cannot vary. Everything which cannot vary is of course commonality. So going back to our two processes, the domain and application engineering processes, in domain engineering, you define the variability, what can vary, and also the commonalities. So you define your core framework, the common shared set of features, but in addition, you also define what can vary. And this has consequences. This has consequences not only in requirements engineering and design, but it has also consequences in testing. And in application engineering, you are forced to reuse these commonalities. So you can't change them, because if you change them, the whole approach will not work. And in addition, you bind the variability, so you bind the variation points to the variance which a certain customer wants. A red car, a green car, a car with 500 horsepower or with 100 horsepower, a sedan or a convertible or whatever you have. So in principle, it's very simple. As always in theory, you define what can vary, what cannot vary, and the rest is commonality. And this is reused across all the products. This is the creative part in domain engineering. In application engineering, more or less in an ideal setting, you just reuse what has been defined above. In reality, it's a little bit different. You also extend things in application engineering, but for the sake of simplicity, we just ignore this today. Let's make the example, a very simple one. Can I have some water? Is that just a bottle of water? Okay, excellent. So you have an online store system, and you have three payment methods: credit card, PayPal, and bank transfer. So these are the three things you want to offer in your product line. And now there are obviously with these three. Thanks very much. With the three different payment methods, obviously you have many possible products. So just one variation, namely the way you pay, and you can have a product just with PayPal, you can have a product with credit card payment just, or with bank transfer, you can have the combination of the two or the combination of the three. So altogether, there are, with this very simple example, 7 possible products, which differ in the way the payment methods they offer. In a typical product line, I know from in industry there are about 100, 150, in some cases even 300 such variability points. So you can imagine the possible products you can derive goes in a very, very huge number. So these are the products which you can do in our simple example, 7 possible ones. And now the question is, what is variability and what is commonality? So there are 3 online store examples with 3 different combinations of payment methods. As you can see, the first one has credit card, bank transfer, PayPal. The second one has credit card and PayPal. The third one, credit card and bank transfer. So the question now is, what is commonality and what is variability? It's very simple. The things shared by all products is commonality. So credit card payment in this case would be a commonality. Even the system can differ in the payment. And the other things, bank transfer and PayPal, which is included in one product and in the other, or both in one, this would be the variability of the product line. So commonality means really this thing is part of every product, and variability means the feature is not part of every product. In our case, credit card is part of every product in this example. You can do different examples, then commonality would be a different thing. And the variability in our example is bank transfer and PayPal. As you can also already see here in this example, it's not so easy to, if you look at a product, and we will see in a minute, also if you look at development models, to identify what is variability and what is commonality, and this is why we need to do something special. So let's look at development artifacts. A simple class model or extract from a class model. There's a German company who builds TV receiver where you can exchange the models like DVDB or DVBS, and also you can choose if you want Wi-Fi or wired, and you have this class model. So if you look at the class model, the first question is, are both DVB models in each product, or has one to be in each product, or can both be in, or must both be in? So essentially, from the class model, you cannot tell. You cannot tell if those are in each product, or if there's a product where only one is in, or a product where only the other one is in, or if both can be in. Same for the network adapter. Is a wired or a Wi-Fi network adapter included in each product? You might deduce from the cardinality constraint above that at least one is included, that's correct, and it's 1 to 2, so you can do whatever you want, but you don't really know if in all product there are both in, or if there's really just one in. So based on the development artifacts, or like a class model, it's close to impossible to identify product line variability. In principle, it's really not possible to see, based on a normal model, what is product line variability and what not. You can see software variability, but not a product line variability. And the more complex the model gets, the more impossible it is to identify what is variability and what not. Next idea, we look at code, a very simple code fragment, just a if then else statement. So you have a navigation system, and there are 3 types of map from South Africa, Australia, and Turkey. I should have said Valencia, I must say. And if you look at that, again, you cannot tell if all 3 maps are included in all products, or if one is at least included in a product based on a statement. You cannot really tell the difference between the products which can be developed if this is a product line under this product line. It's also a very simplified example. Of course, at this example you can guess something, but if you look at normal code, it's absolutely impossible to tell if an if-def statement, for example, is based on a testing primitive or really based on a differentiation of the variability. So again, in source code, looking for variability in source code, it's very difficult. You can identify possible variabilities, but you can't tell what is variable in this product line and what not. So, product line variability, seems not to be an inherent property of the development artifacts, because you can't tell in the development artifact if this is product line variability or not, and therefore you need to explicitly document the variability. This is something which was realized very quickly when people start dealing with product families or product lines. The whole work started late 90s, so 97, 98, there were the first workshops about it. So that there is a need of explicit definition. This was agreed very quickly, especially among the practitioners, not so much among the researchers, but the practitioners immediately recognized, yep, we have to do something about it. And the question is now, how to do this? The thing which also there was an agreement very quickly about are the key modeling concepts, which is like entity relationship model, very simple, variation points, what varies, we had this before, the color, the variance, how does it vary, so the type of the color, and then there are essentially two ways. The first one was the more natural one, you made an integrated representation of variability, which means you use your development model, your source code model, your source code and other artifacts, and you just put into this model what can vary and what cannot vary by making this explicit. We will see a few examples. The idea that you define a separate model for the variability was introduced later on, and we will see about the benefits of the integrated and then the benefits of the orthogonal approach, which even offers more benefits than the integrated approach. Let's start with the integrated. Feature models again, since nobody raised their hand was a feature model. This is an example for a feature model, a simplified one from automotive domain about the wipers, the windshield, the front and rear wipers. In a feature model, as you can see here, there are also only a few concepts, namely the observable features. We have a front wiper, and then there is this differentiation of a feature into, call it sub-feature, and there are small bubbles and no bubbles. A bubble, so a circle which is not filled, means that this is an optional thing. So for example, on the right upper side, you see the rear wipe, and the rear wipe has this small empty circle, which means this is optional. Why is a rear wipe optional? Well, of course, not every car has a rear wipe, but every car has a front wipe. The same, for example, for on the right-hand side for the interval wipe or for the steady wipe. These are also optional features, whereas if you have a rear wipe, it has to have a wash and a type rear wipe feature. This is the example, not, but the feature model is from Carl Chang, who is now since many years back in Korea. On the left-hand side, the front wipe is mandatory, so you can type the wipe, interval wipe, you have a warm water wipe for some more pushy cars, you have automatic rain wipe nowadays in many cars, and you have maybe an adaptation of the wipe function depending on the speed you are going. So when you look at this feature model, you can identify commonality. This is the thing which cannot change. And so these are the features which are common to all products. And then you have the product line variability, which are the features which are not common to all products, which can be included in a product or which cannot be included in a product. This is one way for integrated modeling variability in features, that you differentiate between must features, which have to be included in every product, and features which have not to be included in every product. Use case diagrams, I guess most of you know as well. The typical extension was that you introduce stereotypes, variation points, and variance. So like you have an open door function, and you can open a door from your office room by entering a pin, touching a scanner, or place your identification card in front of a card reader. And by introducing stereotypes, you can define in this model that the open door is a variation point. It's actually not an open door, as we will see in a minute. And you have three variants, and a pin, touch scanner, and replace reader. In this case, everything is product line variability, so in this simple example, there is no commonality. This was one way to do it in use case diagrams. A more advanced way was to really differentiate what is a variation point. So what can vary, namely the door lock, as you can see in the middle. And then you have again the variance. You don't have to put a stereotype because since they are allocated beyond variation point, you know that these are variance. So the variation point and the variance. And in this case, you can see the commonality is that every product has something to open the door, and it can vary in the way the door lock is activated or deactivated. Same in class diagram, simple class diagram, again with stereotypes, so a file, a binary file, and an ASCII file, and then you can have different ways of displaying a file, and again you have commonalities and variability. So this was the thing which really, really quickly emerged in the early 2000s, and most of the people were happy because now you can look at your development artifacts and you immediately see what is variability, how your product line can vary or not. But there were some problems. So in each of the artifacts, the variability is documented differently. Like for example, a variation point is either a stereotype or not represented at all, like in a use case diagram. The variability information is depicted in a class, in a use case, or in a sequence. In the simple example, you still can identify commonalities, but in real industry example, there was a huge problem in identifying how all this different type of variability fits together, or what realizes what, or what is the same and what is different, and keeping it consistent was close to impossible. So how you keep such information, which is spread across the model, consistent was one of the major problems. Nevertheless, there have been significant benefits of this integrated variability modeling. So you explicit document variability, so you were able to talk about. When you do this, up a certain people were able to discuss, is this really a variation point or is this not a variation point? Before, this was impossible. The drawbacks essentially was the identification of the variability across the different artifacts, if it's the same or not a uniform range, so everybody who looked at the variability has to understand the variability definition in the different model. And a drawback which was only recognized when the new way of modeling variability was introduced was that you always have to talk about solutions. You could only define variability when you already define the variant. And you have to have a class model, you have to have a use case model to be able to define your variability in these models. And this was something which was recognized later on also as a key drawback, because you always were discussing more about how to do this and not what should be there. So this was the reason why we introduced the orthogonal variability model in early 2002 to 2003. And the principal idea behind the orthogonal modeling of variability, and this is the way most people do it today, at least most people I know, obviously this is a little bit biased. And the principal idea is you define a separate model, orthogonal variability model, like you define a class model, a use case model, a scenario model, a test case model, so a separate model, dedicated model. And then you relate this model to your requirements, design, implementation, and test artifacts. This is the principal idea behind. And how does this work? As simple as entity relationship diagram, much simpler than a UML class model. So two concepts, variation point and variance. This is the notation for a variation point. It's a triangle. For the variance, it's a rectangle. Then you have what we call variability dependency, which allocates variance to variation points. So in this case, variant 1, 2, and 3 is located to variation point 1. And the fourth thing you really need is the alternative groups, where you can define a min-max relation. So you can say this variation point, if it's included in the product, has to be bound with 1, with 2, with 3, can be bound with 5 variants. So for example, 1.3 would indicate that you have at least bind 1, but you can bind up to 3 of these variants to the variation point. in application engineering when you develop a product. So in domain engineering, you define this model, and in application engineering, you use this model to bind the variability based on the customer or market-specific needs. With our color example, we have a variation point color, and you have three variants, red, black, and white, and you have a 1-1 because a color can either be black, white, or red, as defined in this model. There's a lot more behind this. I don't go into much detail how these models are defined or how variability modeling works in detail. There's a book where you can read if you are interested more about this. What I want to do, just to illustrate how important this differentiation between what is a variation point, what can vary and what not is just to illustrate this with the car example. So in this example, you just see a car can have one color, red, black or white. In the other example, and there has been such a car, at least in Germany, this was sold by VW, there was a different type of variation. So there was a different definition what can vary. They defined that the roof color, the front color, the black color, the left door, the right door, etc. color can vary, and that each of them can have different colors. And by this, of course, a car can look different. This is the easiest way to understand that the impact of defining in a product line a variation point in a different way than in the other example. So in this example, you can have very, very different looking cars. And it really depends on the definition of what can vary. And the same is in software. You can say that nothing can vary, then this thing is all the same, or you can do it at a much more fine granular level, and thereby you can allow much more variability than in the other case. The problem which comes with this is also very simple. The more variation points, the more variance you have, the more complex gets the development, and the real impact, the real complexity you get with this is in testing. So the more variation points you have, the more complex the tests are. And in single system development, you already know you can't test everything. In product line engineering, with traditional test approaches, forget about. So you have to think about something different. There are solutions to that, which we will not talk about today, but maybe if you can, as a takeaway, take with you that the variation points really determine the complexity of the testing, not so much the functionality in the product line engineering. This is something I think which is a key insight. So if you define variation points from a management perspective, it's very, very important not to define too much. For the market, we want to define a lot, but for managing the complexity and especially for testing, but also for maintenance, it's important that you restrict the product line to the variation points which are really required and not the ones which you could imagine somebody might use in the future. So in the simple example again, you see the impact. So the definition of variability points has a key impact on the differentiation. And if I define variability for a product, I do this based on market needs or customer demands or whatever, but not based on technical realization. So I want to define variation points, what can vary, independent of how this is realized. And this is possible with the orthogonal variability model. In the other case, it's not possible. So now we have this orthogonal variability model, but we still have the development artifacts. And the question now is, how does this relate to each other? I will illustrate this on requirements and also on a simple test case. On the right-hand side, you see the requirements. 330, the home security system shall be equipped with black and white cameras. The security system shall be equipped with color cameras. The cameras of the home security system shall be capable of infrared shooting. And on the left-hand side is what the people have defined independent as variability, namely camera type can vary black and white and color. And now you relate this variation, the black and color, to the requirements where this is specified. You might have to refine the requirements. So, for example, the black and white to 330, the color to 331. And by doing so, you have identified what can vary in the artifacts, namely the requirements 330 and 331. And implicitly, you have also identified what cannot vary, so what is the commonality, namely all the requirements which are not related to any variance in your variability model. So by simply assigning the variance to the development artifacts, you identify in the artifacts what is variable and what is common. If you change the variability model, of course the association change, and thereby it changes what can vary and what cannot vary in terms of requirement, but also development artifacts. So this is with the requirements. Of course, a simplified example, same with a data flow model, also simplified. Home security, variation point, motion detection or camera survival, and data flow diagram on the right-hand side. It's not so important what's modeled there. It's more important that you again relate the product line variability to, in this case, but also in the case of requirements, to a set of the development artifacts. In this case, the selection of the yellow concepts like the data store and the process and the data flows between. And to the motion, it's the one below, and again then you see what is commonality, namely the alarm detection, and what is variability. In this simple example, this looks very, very simple. In a real modeling context, this is a little bit more complex, and a typical rule of the thumb is that the commonality is about 50 to 80%. So there's normally more commonality than variability. Again, you can see by relating the variance to the data flow diagram concepts, you have defined what is variable and what is common. Same you can do with use case diagrams. I'll make this a little bit quicker. And you can also do this with scenarios, for example the door lock, which we had before, with a keypad or a fingerprint as two variants, and on the right side a tabular scenario which defines how you interact with the door. You have the keypad, the inhabitant enters the pin as variability, as well as the inhabitant touches the finger sensor, and the rest of this diagram is commonality. And depending on which variant you have bound, you test one or two. If both variants are bound, you have to make an alternative scenario. So also in this case, just by relating the variants to the artifacts, you identify what is product line variability in the artifacts and what not. What not means what is commonality. And you can do this with test case scenario in the same way. So again, the door lock example with the keypad, the magnetic card and the fingerprint, and you can relate the variability information to this, and then you see what is commonality. This is just as an illustration. In practice, it's much more complicated because it's not a one-to-one mapping, and it's not really done the way it's illustrated here. This is just for illustration, that you know by relating the two things together, you can identify what is product line variability and commonality. There have been several PhD theses which work this out in detail, and one of this approach is even used within Siemens. So in principle, the key idea behind this in the relation. And this in the relation has several advantages. First of all, you have a uniform definition of the variability across all your development artifacts. You have it separated from the development artifacts. And surprisingly, when you do this in industry, people have a different focus. So when you sit with your stakeholders and you define just variability models, no features, no functions, no nothing, just a variable. What can vary? And then later on, how can it vary? And this is where it goes in detail of the feature. Then you recognize that also the communication is very, very different than if you would have not done this in this way, that you have this explicit modeling concepts. A key benefit you get by this principle that you have a variability model and then the development artifact, which is illustrated in this picture, like the use case, the scenarios, and the class model, is that you can now identify which impact a variant has in which of those artifacts. Here again, very simplified, that the PDF, for example, is the PDF in the class model, it's the open document in the test case scenario, and it's the display document in the use case scenario. And the MP3 with the blue lines is related to other concepts. And what you can do now is, if something changes, so if somebody modifies a use case, you can identify where this modification has an impact in the variability model, and thereby you can identify which potential other artifacts have to be changed, or maybe not to be changed, but at least you can select the artifacts which are in principle, which could be influenced by such a modification. So you get the thing traceable and also much more manageable. There is also an additional advantage, which I personally think is a very nice one. So you have the variability model, and you have the use case diagram, and you have this interrelation we talked about. And what you can do now with each model is you can generate the integrated product variability model. So, because you don't want that your developer always has to look at a use case model, you have to follow the interrelation, then look at a variability model, what varies. Based on this information, you can, every second, every 2 seconds, every day, whatever you want, you can generate the integrated product line variability model. So you can integrate the variability modeling into the model again, so like we explained at the beginning, with the key advantage that there is one model behind this, which assures consistency across the artifacts and thereby ensures that you consider the same type of variability in the different model. This is a very nice advantage. Of course, you need tool support for this, but in this case, the integrated modeling is more or less that. So you don't allow that people change this in a model because the way back is a little bit more complicated, but when you make changes in a variability model or in the association with these links to your artifacts, you always can generate a new version or better say, the actual version of the integrated variability modeling view in your different artifacts. To summarize, I personally think that this product line variability and the explicit documentation of variability is something which will emerge very, very, very quickly. You have it in many, many domains, in the car industry, in the mobile industry, in the medical domain, in a lot of domains, and without a common core, a common managed set of features which don't change between the products, the complexity of the software products just gets too big and thereby too expensive to pay the individual developments. So it's something which will spread over and which has significant consequences for testing. Just a very small example. The key difference between normal testing and product line testing is that if you exclude a variant, you have to make sure that this variant which you exclude in your current product has no side effect to any other function. So that there is nothing implemented in this variant which has a side effect on the other functions you have in the product. So in principle, you have to test all the products again and again and again. There are some more clever approaches, but it's not just that you leave something out. What you can leave out can have side effects to the other things. And to manage the side effects in testing is not really that easy. But if you define the product line variability in the way we have discussed, if you relate it to your test artifact, at least you know what can vary, and then you can do additional investment if a certain binding of variability has side effects, which you have to consider separately during testing. The orthogonal variability model is something which is widely used today and which was adopted by many people with a little bit different notation, but it's a very simple model and therefore also easy to be done. And even if not related to the development artifacts, it offers the advantages that at least the tester know what can vary and how the binding in a particular product is, and therefore can make certain adaptation to his test cases. There is a lot of reference that the slides will be distributed, of course, where you can look for detail, and there is also this Kang 9090 is the thing about the feature model. If you don't know, really have a look at it. I think it's a thing which is also heavily coming up. And we do have 3 minutes for questions. If there are no questions, then you can enjoy your lunch.